Hello again. This video is in many pieces because I've been making it during the day, during my prep period, with various distractions throughout. So this will be the final video for circular motion and gravitational force. And we ended on slide 46. So with conceptual questions. Which is stronger, the Earth's pull on the moon or the moon's pull on the Earth? You have to conclude that they pull on each other equally because they're a Newton's third law action-reaction pair. The Earth pulls on the moon, and the moon pulls back on the Earth through that gravitational interaction. If the distance to the moon were doubled, then the force of attraction between the Earth and the moon would be which? So how does the force of gravity change if the distance is doubled? Since the distance between the objects is squared, it's an inverse square law. If you double the distance, the force decreases to a quarter of its original value. So if you weigh yourself on a scale inside an airplane that is flying with constant speed at an altitude of 20,000 feet, how does your measured weight in the airplane compare with your weight as measured on the surface of Earth? And imagine that it's a very accurate, precise scale. You would conclude that at high altitude, you're further away from the center of Earth, so the gravitational force on you would be ever so slightly less than when you're on the surface of Earth. The moon does not crash into the Earth because which? None of those answers are acceptable. The moon does not crash into Earth because of its high speed. It's moving in a circular or almost circular orbit. If it stopped, it would fall directly towards Earth, but with its high speed, the moon would fly off into space if it weren't for gravity, providing the centripetal force that keeps it in its circular path. So finally, we're going to end with a calculation example. Calculate the speed of a satellite moving in a circular orbit about the Earth at a height of 4,800 kilometers. So we'll start with the theory behind this. We know that centripetal force, or we now understand that centripetal force can be expressed as mass times speed squared divided by radius. And in a circular orbit, that centripetal force is equal to the pull of gravity. So mv squared over r, this would be the force on the satellite. I think I just misspelled satellite. Switch the double T's with a double L, is equal to the force between the satellite and Earth. And we can now express the force between the satellite and Earth using Newton's law of universal gravitation. So mass of the satellite, lowercase m, mass of the Earth, specified by subscript e, divided by the distance between the two squared. Now we can simplify this equation. There's mass of the satellite on both sides of the equal sign, so we could factor it out. There's also a radius or distance between the two objects on both sides, and we can factor one out on the left side and one on the right side. So now we can say that the velocity of that satellite, the velocity of the satellite in its circular orbit is equal to g times the mass of the Earth, divided by the distance between the satellite and the Earth. And then, of course, for v, we take the square root. So now we need to look up a few quantities, right? We need to know what that gravitational constant is. We need to know what the mass of the Earth is. And then this satellite is in a circular orbit at a height of 4,800 kilometers. So this is going to be radius of the Earth plus 4,800 kilometers. This is the mass of the Earth. And this is gravitational constant. So you can Google those. You can also look them up in your textbook. We have V equals square root of, it's going to be hard to fit all those weird values in here, but G is 6.67 times 10 to the negative 11th. The only way I can fit this on the page is to not include the units. Units of G are newtons times meters squared divided by kilograms squared. Then I'm going to multiply by the mass of the Earth, 5.98 times 10 to the 24th. That's in kilograms. And then the radius, so the distance from the center of the satellite to the center of the Earth, is going to be the radius of the Earth, 6.38 times 10 to the 6th meters, plus 4,800 kilometers, so 4,800 meters. We've got to be all in SI units. So I'm going to use the solutions manual, and you'll let me know if the answer is not 5.97 times 10 to the third. Whoops, I didn't actually write the whole thing. Meters per second. So 5,970 meters per second. It's quite fast. But being up in being in Earth orbit, at least, there's almost no resistance. So the satellite can travel very fast without the effects of air resistance or the frictional forces. I hope you're having a nice vacation.